Good afternoon, physics class. I know we ended part A in the middle of a question. Sorry, I got a phone call, and so I'm going to pick up with part B of this video, picking up where I left off on the last video. As we tackle this problem, one of the things we're working on trying to find is the amount of time it takes for our bullet to touch the ground. So I left off by saying that 250 times the sine of 65 was, let me get the right color here, 226.577 t plus 275. And we'll get negative 4.905 t squared over there. Now again, this is going to be something that we're going to have to solve as a trinomial. So we'll use the quadratic equation to find t equals negative b. So it's 226.577 minus, and I know the quadratic equation says plus or minus, but the only way we're going to get a positive answer is if we use the negative version. We've seen that a number of times this year, so I don't want to go into explaining that again. So b squared minus 4 times a, which is negative 4.905, times c, which is 275, all over negative 9.81. Okay, so we'll start with our order of operations. That means I want to take my 226 value, 226.577, and I want to square that. So we'll get negative 226.577 minus the square root of 51337, and it's going to be plus because I got a negative times a negative, and I'm going to do 4 times 4.905 times 275 gives me 5,395.5 all over negative 9.81. So then we'll take our 5,395 and we're going to add it to 51,337.1369. And we get negative 226.577 minus the square root of 56,732.6 all over negative 9.81. Take the square root of that, and we'll get negative 226.577 minus negative 238.186 all over negative 9.81. So now I'll combine like terms, 226 and 238, all divided by 9.81. We get a positive answer. T is going to equal 47.376. That's one of the answers, how long it took. So if there were 3 significant digits in the problem, remember angles don't count. We stated at the beginning of the year. So 275 is going to be the significant digit I'm going to pay attention to for this class. So it's 47.4 seconds to get out of the way. I know that was the last part of the question that was asked here, but I wanted to find that first because that's going to allow me to determine how far it's gone. That's how long it's going to be in the air, is 47 and almost a half seconds. So if I want to calculate the distance traveled, I'm going to use the position equation again, but this time in the horizontal. So I put x instead of y this time. X final is going to equal, again, acceleration times time squared over 2 plus velocity initial times time plus position initial. Now, remember, all the acceleration in the previous part of the problem came from gravity, that negative 9.81 value. gravity doesn't apply left to right. It only applies up and down. So there's no accelerant for the horizontal forces. For horizontal, the initial velocity is found by 250 times the cosine of 65 times the time, which we just calculated, that was going to be in the air for 47.5 seconds. And the initial position, don't get tricked into putting 275. The initial position is 0. Because again, we're talking about left to right, and we're not given any reference, so we're going to use 0. So we have 0 at the front, 0 at the back. That makes this a whole lot easier than the last question, part of the question we were doing. But we had to do that in order to get to this point. So I'm going to do 47.36 times 250 times the cosine of 65. When I plug that into my calculator, I'm going to get the final position, and is going to be 5,005.5 meters. Apply significant digits of 3. I'm going to get 5,010 meters. So the bullet's going to travel 5,010 meters, and you got 47. There's going to be 47 seconds until it hits the ground. Okay, next question that I'd like to tackle is find the final speed. Now, I'm only going to worry about vertical speed here. I'm not going to pay any attention to the horizontal speed. So I'll say use the motion equation. It says velocity final in the vertical direction. So I kind of preface that by saying velocity final vertical direction equals velocity initial plus acceleration times time. So the velocity initial in the vertical direction is found by 250 sine 65, which we already calculated over here. And acceleration, and remember we're talking about vertical, is negative 9.81 times the final time is 47.36. Okay, we do a little bit of math. I already calculated 250 sine 65 to be 226.577. 9.81 times 47.36. Okay. 97.36 equals negative 464.6016. So now I'm going to combine those terms, and we'll get negative 238. So my final velocity in the vertical direction, up and down, is equal to negative 238.0246. Apply my two significant digits, so we're going to get equals negative 238 meters per second. That's this part of the component, like the directly perpendicular to the ground velocity. There would also be a horizontal velocity. You calculate that the same way. The only thing that's going to be different is you're going to put cosine into the problem, but then you have something in rectangular form. You got to convert it back into polar form. Again, I'm just setting that up. We'll probably tackle it next week. So the last part of the problem is, what is the maximum height up here? And so we've learned already this year that what we do is we're going to start with the motion equation for velocity final. So vertical velocity final at the maximum height is equal to the velocity initial plus acceleration times time. The final velocity is equal to 0. The initial is, again, equal to 250 sine 65. The accelerant in the vertical direction is 9.81 meters per second squared, and t is the time. So I could just move 9.81 to the other side, and we already calculated 250 sine 65 earlier in the day, and we got that to be 226.577. Save ourselves the work by reinventing the light bulb. So we're going to take 226.577 and t magically disappeared. It shouldn't have. It should be right there. And we'll divide that by 9.81. And we're going to get the time till it reaches its maximum height to be 23.965 seconds. Okay, so now we're going to plug that into the original equation we had right at the beginning of the day, where we had velocity or position in the y direction final equals negative 4.905 t squared. And just in case you wonder where I'm getting this equation from, it's right over here. So t in this case is 23.965 squared plus 250 sine 65 times 23.965 plus the original height of 275. All right. So we're going to do 223 point, and that should be a zero in there. So 23.09. So I'm going to square first, order of operations. I'm going to multiply by 4.905. So I get negative 216.57. And then 250, we already have determined to be 226.577. That's played a lot into this problem. Times the 23.0965 seconds. Gives me a positive 5,233.135 plus 275. Now we'll just combine all our terms. So I'm going to start with the 5,233. I like to always start with the positive. And then add the 275. And then subtract the 2,616.57. Gives us our y final, or y max. I shouldn't say y final, because y final is when it hits the ground. The y max is 2,891.5656 meters high. All right, and so if we were to put where that ends up happening, remember we're using 3 significant digits. It has a grand total height of about 2,890 meters. Just a little bit of this is a lot of the math that you need to do for your end of the year trebuchet project. I might be adjusting some of the trebuchet stuff that I've been working on to for the date that you're gonna have that done, but I'm hoping you're working on maybe a small trebuchet or a big trebuchet, something, maybe a project with your dad or someone who might want to help you, or you can do it yourself. But looking forward to see those. This is a lot of the math that comes into that. All right, let's move forward. Let's keep going. Timmy pedals his bike so that it accelerates at a constant rate of 0.025 meters per second per second. Find the angular acceleration of the 0.5 meter radius tire. Find the angular speed after 14 seconds if the initial angular speed is 0.5 radians per second. What was Jim Bob's? Oops, he magically went from Timmy to Jim Bob. This is Timmy's bike. All right. So his angular displacement after 14 seconds. So the first part we want to work on is A equals R alpha. Linear acceleration equals the radius times the angular acceleration. Linear acceleration, it says, is 0.025 meters per second. That's the A value. And the radius is given to us as 0.5 meters. So we could put that right into the problem. We can say 0.025 equals 0.5 alpha. So we go 0.025 divided by 0.5, and we get 0.005 radians per second squared as being alpha. As I look up at the problem, I see 2 significant digits. So I'm going to go alpha equals 0.05 1.50 radians per second squared in my answer set. All right. So now it says find the angular speed after 14 seconds if the initial speed is 0.075. So we're going to use the distance equation, but we're going to make it an angular distance equation. So we'll say alpha times squared over 2 plus omega initial times time plus theta initial equals theta final. Oops, that's for problem part 3. Part 2 is omega final equals omega initial plus alpha times time. And angular speed plus angular acceleration times time. So our original angular speed, our initial angular speed is 0.75. Our angular acceleration is 0.05. And the time is 14 seconds. All right, so we can get our handy calculator. 0.05 times 14 is 0.7 plus 0.75. So plus 0.75. Our final angular speed isn't very fast. 1.45 radians per second. 2 significant digits in my answer. Final at 14, let's try to be clear, is 1.5 radians per second. And then I want to go back to this equation. This is for part C. And so my final at 14 seconds will be found by 0.05 times 14 squared over 2 plus my initial angular speed is 0.75 times our 14 seconds. And I'm not given an initial angular position, so we'll just say that that's 0. All right, so unit order of operations says that I should do my square first, then I'll multiply by 0.05, and then I'm going to divide by 2. So I'll get 4.9 plus 0.75 times 14 is 10.5 plus 0 equals angular displacement. So our angular displacement after 14 seconds equals 4.9 times 10.5. That's not very far. 15.4 radians. Apply significant digits. Theta final at 14 seconds, or the displacement of it, excuse me, let me get back here, is equal to 15 radians. All right, thank you for the lesson. Sorry it was in 2 parts. Have a good evening, and we'll see you tomorrow.